So this is a review for exam 2. Review for exam 2. So I'll start with the conceptual map. So for exam 2, we will be dealing only with kinetics of particles, and so it's only for the particle, not for a rigid body. And kinetics involves forces, the cause of motion, right? The cause of motion. Whereas kinematic, which we did before, involved the geometry of the motion. So sometime we may have to use the basic Newton's law, which is summation of force equals to ma. Sometimes you have to use work energy principle, and sometimes you have to use impulse momentum principle. You should know when to use each one of these. It makes it a lot easier when you choose the right principle to carry out the calculation work. Okay, so for instance, for a summation of f equals to ma, usually the most important parameter is acceleration. Okay, and for work energy principle, this work done here is force dot ds. So displacement and kinetic energy are velocity. So the displacement or the position are the most important parameter. Whereas in impulse momentum principle, the time is the most important parameter. So based on what is given in the problem and what has been asked, you must choose the right equations. So you could do for the linear impulse momentum principle or angular impulse momentum principle. And then and for the linear impulse momentum principle, um, the example being the impact, and we'll talk about central impact and then oblique impact. So if you try to look for the second law, you can do the problem using rectangular coordinate system, NTB coordinate system, or cylindrical coordinate system. Whenever you do this problem, you must, I told you in the class as well, you must make always free body diagram, not only free body diagram, as well as quantity diagram. So this is like half the problem is solved if you make the right free body diagram and quantity diagram. You can do the problem in rectangular coordinate system. Again, this is the basic summation of f equals to ma is the basic equation. This is a vector equation, but whenever you solve the problem, you always write in the form of scalar. So in xyz coordinate system, summation of fx equals to max, summation of fy equals to may, and summation of fg mag. If it's two-dimensional problem, we will just use this one. If it is NTB coordinate system, normal, tangential, and binormal coordinate system, in the tangential direction, summation of ft is mat. In the normal direction, summation of fn is man, and in the binormal direction, it is 0. Okay. Similarly, so and we know what at is from kinematics, and we know what an is. At is, so you have dv by dt, and if it is a function of s, then it is v dv by ds. An is v squared by rho, right? And if it is a cylindrical coordinate system, you could write the equation accordingly. Summation of fr equals to mar, summation of f theta equals to ma theta, and fg is summation of mag. So depending on what is given in the problem, you have to choose the right coordinate system and accordingly solve the problem. But the most important thing is you must make the free body diagram as well as the kinetic diagram when you solve this problem using this coordinate system. Okay, and you have to choose the right kind of coordinate system for solving different types of problem. Other way to solve the problem is work energy principle. As I said before, when you have two locations in space and want to find out velocity, we usually use the work energy principle. And for the linear impulse and momentum principle, the time is the key parameter. So again, everything is for particle. Once the problem is given, you need to decide which equation to be used based on what is given in the problem and what has been asked. And for angular impulse momentum principle, so this is the equation: initial angular momentum equals to angular impulse equals to the final momentum. And if this angular impulse is 0, then the initial angular momentum becomes equals to final angular momentum, and we call this as conservation of angular momentum. Okay, and a very classic example of linear impulse momentum is impact, and we'll talk about central impact and oblique impact, and you should know which equation to be used for the central impact. So central impact is if the velocity direction is along the line of impact, then we call central impact. So in that case, we'll be using conservation of conservation of um, conservation of linear momentum as well as coefficient of restitution equation. Okay, and for oblique impact, we will use two more equation. Along the line of impact, we use the same type of equation, but for perpendicular to the line of impact, we use the momentum of each particle are conserved. So you will have four equations and four unknowns by which you can solve it. So this is the overall picture in terms of the content for the exam too. Okay, so this is kind of summary. We use this new basic Newton's second law. Again, this is a vector equation, and then impulse momentum equation is also a vector equation, but the work energy principle is a scalar equation. So sometimes this is a modified form of work energy principle which relates to the conservation of energy, and this is not a velocity, this is a potential energy. So initial potential energy plus kinetic energy equals to the final potential energy plus the final kinetic energy. So you use this one when all the forces are conservative. So this is easier to use. And then work energy principle, the key parameter being S means the different position and V is the velocity, and linear impulse momentum principle, the time is the key parameter. So that's how you make a decision and solve the problem. For rectangular coordinate system, as we discussed before, so these are the equations for rectangular coordinate system. So one example could be, this moves in xy direction. So for this problem, you can use rectangular coordinate system, but make sure whenever you are solving the problem, you must make the free body diagram and then kinetic diagram for whatever the body. If you are doing for A, then you need to consider what weight is, and then the tension, and then you need to consider the kinetic diagram where max, and then normal force. So, and also if you see like the pulley connected by rope, then you must use the connected bodies principle that relates with the kinematics, because you will be getting one more equation from there. Since we are interested in acceleration here, so you need to find out the relations of acceleration of this body with this one using kinematics. So you start with the total length of the rope and then find the total length. If you take the derivative of that, you get velocity relationship, and if you take the derivative of that again, we get the acceleration relationship, and you are getting more extra equation. So that is very useful. And if the weight is given, remember, if you want to find out the mass, divide by 32.2 feet per second square. So as I said, if connected bodies need to find the relation of this acceleration between body using the kinematics. So you start with the total length of the rope, and then if you take the derivative, it becomes the velocity relationship. If you take the derivative of that again, it gives you the relationship for the acceleration. So it may be convenient sometime to use anti-coordinate system as well, like the problem we did before in the track. So like here, if the car is moving in the racetrack, so it is kind of inclined. So you may be asked a problem related to this type of problem. So here it is kind of inclined. The tangential direction is always tangent to the part, so it is perpendicular to the screen. normal is somewhere here, and then binormal is this. So in this case, we tend to, you know, have the component of all the forces in normal and then binormal direction, and then find out summation of Fn equals to Man, and summation of force in binormal direction is 0. And again, you have to make the kinetic diagram of this one as well. This is Man, and then there is no acceleration in the binormal direction, so this should be 0. And then equate to it, break the component of forces in this normal and binormal direction. It's hard to break the component in the tangential direction, that's why we are doing in the normal and binormal direction. So this type of problem could be asked here. I think in the class we did derivation, but you can be given problem with or without friction and ask you to find out the velocity, the optimal velocity. The other type of problem based on work energy principle. Again, remember, when the position of two bodies are given and we are interested in finding the velocity, we use the work energy principle. So in work energy principle, so if you see here, the equation for work energy principle is this one, and this is the work done. So work done, in this case, you have to make the free body diagram and see the component of forces in the direction of motion. We are only interested in the component of forces in the direction of motion. But sometimes you may have to use, a summation of Fy equals to 0 to find out the unknown as well. It's not like we just use one equation. So if the force and then displacement are in the same direction, it is positive. And then if force and displacement are uh, in the same direction, it is positive. If they are in opposite direction, then it is negative. That's the sign convention which you will be following it. So I think in the class we did a problem that related to this one. So what in this problem we need to find out the distance s when the block is stopped. So what you need to do is, this is the direction of motion, so you need to get the component of all the forces in the direction of motion, and then for each forces, see whether the work done is positive or negative, and then carry out the calculation. If the normal force is required to be is unknown, then in such cases you may have to use maybe summation of Fy equals to 0 and find the normal force, and then go from there. It depends on how many unknowns are there, and then based on that you have to carry out the calculation. So in this case, it's a smooth lane, so there is no friction. So if there was friction, mu k n, then first of all you need to find the normal force, maybe using this one, and then you can find the work done by the friction. But in this case, since it is smooth, this is neglected, so you don't have to worry about the normal force which acts perpendicular to the direction of the motion. Okay, so we did this one. So that's related to the work energy principle. Then and sometime we may use conservation of energy. So T1 plus V1, this one is a potential energy, so this not a, so big V is a potential energy. This equals to T2 plus V2. This is used when only conservative forces are given. So conservative forces only depend on the initial and final condition. It does not depend on the path followed. Okay, and you need to follow the proper sign convention. Like conservative forces like gravity and then spring force half ks square. So these are the conservative forces, work done by the conservative forces, because this only depends on the initial and final position. For the work done by gravity, for sign convention, you need to choose a datum line, and anything above is considered to be positive, anything below is considered to be negative. Um, uh, and then for the spring, it's always positive, because this is s here is the deformed distance from the on stretch position. So the square of that would be always positive. So if only conservative forces are given, then it's easier to use the conservation of energy principle. So this is the conservation of energy principle. So I think we did this in the class. So here at the beginning it is in position A, and after some time it is in position B. The forces acting here are the spring force and then gravity. So we can easily make use of conservation of energy principle to find out the velocity at point V. Um, so principle of linear impulse and momentum. So for linear, so this is the basic equation. If you replace that a by dB by dt, it becomes this. And then if you simplify it, so this is called linear impulse, and then this one is change of linear momentum. So this is what we call linear impulse momentum principle, and the key parameter being here time and then velocity. And like work energy principle, you have to be careful whether you can have this force outside of the integration sign or not. Sometimes if the force, like in the previous case, if it is a function of displacement, you need to integrate. In some cases, if force is a function of time, and again you cannot have this force outside of the integration sign because it is a function of time. So if force is a function of time, you need to integrate and do the manipulation. But if force is constant, if the force is constant with the time, then you can always have this force outside of the integration sign. So this is the summation of all the forces acting. And for this one, you need to make the um, impulse, initial momentum, and final momentum diagram, as well as initial momentum diagram, final momentum diagram, plus the impulse diagram. And then you can write this equation. Again, these are vector equation, but you can always write in the x direction, y direction, and then solve it. So in x, y, z, these are the equation. um, So here, if you see here, force is a function of time. So whenever you write summation of fx dt, then integration, so this is not a constant. So this relates to the area under the plot. So that's the key takeaway from here. I think we did this problem in the class. So this is area under the plot. And you need to be careful with the unit of the force and then time. A very common example of linear impulse momentum principle is central impact. So in central impact, when the two bodies are colliding along the line of impact, so line of impact means when you connect the center of mass of the two body, it becomes line of impact. And if you see the direction of velocity, they are in the direction of line of impact, we call as a central impact. If that is the case, you have two equations. Conservation of linear momentum, so that means the initial momentum equal of two bodies, colliding body, this equals to final uh, momentum, that is the momentum after collision. And another equation is related to coefficient of restitution. So it's a coefficient of restitution. So you have two equations, and we are interested in finding, so this is the equation for coefficient of restitution, in which this is the velocity of separation and this is the velocity of approach. Remember, if you have here v2 here, vv here, then you should have a here. So you should take that into consideration. So you will have two equations, and you usually maybe we are interested in finding what would be the velocity of the impact, and by solving these two equations we can find out the velocity after the impact. In some problem, maybe the final velocity is given, and then you maybe have to find the coefficient of restitution as well, so it can be given other way. But remember, you must follow proper sign convention. That's very important. Proper sign convention. You must follow proper sign convention, and these minus signs come from the formula. So depending on which direction you assume it to be positive or negative, you must follow the proper sign convention. So this is an example which we did in the class. So two bodies, we have been asked to find out how much is the velocity after impact. So we have these two equations, and then two unknowns which you can solve it. So this is for the central impact. And for the oblique impact, Oblique impact means if you have two bodies, so the two bodies, and this is the line of impact, this is the directional line of impact. If the velocity of one or both the bodies are not along the line of impact, so direction is not along the line of impact, right? So this kind of impact is called oblique impact. And if you think, you can break this into two components, along the line of impact and along the direction perpendicular to the line of impact. Along the line of impact, you can still use the same equation, the along the line of impact, uh, linear momentum is conserved, and the same coefficient of restriction equation. And along the direction perpendicular to the line of impact, the momentum each particle is conserved. So you have four equations and four unknowns by which you can calculate. Okay, so that's about the linear impulse momentum. For angular impulse momentum principle, it's very similar again. In this case, instead of linear momentum, you have angular momentum, initial angular momentum, plus this is angular impulse, and then this one is the final angular momentum. So in this case, if the body is kind of rotating, not along its own axis but along certain other axis, then you can make use of angular impulse momentum principle. So so when you have those kind of problem, you need to take into account all the bodies into account. And then this one is the moment. So if this is the axis at which it's rotating, moment means force multiplied by the perpendicular distance. Although this is a vector, you are just considering um, the planar motion. So maybe it is rotating about this axis, so it becomes a planar motion, not the three-dimensional motion problem. Okay, so like here, again you have so the force 10 Newton is applied here, 10 Newton is applied here, and then in this problem the moment is a function of time. So if it is a function of time, so this part summation of mdt plus HO1 equals to HO2. So here this is a function of t, so you need to integrate that at dt. You cannot have outside of the integration sign and carry out the calculation. So that is important. And also you need to find the moment of these forces, and you have to follow proper sign convention, whether clockwise is positive or anti-clockwise is positive, and then go from there. Okay, so here since it starts from rest, initial angular momentum is 0 because mv, and then mv r1, the velocity is 0, so this becomes the initial angular momentum 0. And then you need to find the moment due to this force, so this force and this force, and then both are in clockwise direction, so it's 2 times the force multiplied by the perpendicular distance, and then this relates to this moment acting. Again, you cannot have this outside of the integration sign, the reason being it is a function of t, and this one is after a certain time, and so after the calculation you get the final velocity. So that completes kind of summary.